Hello everyone, my name is Devnandan Kumar and I am currently pursuing BTech in Polymer Science and Technology. In today's videos, I'll be discussing a few important concepts from testing and characterization of polymers. These topics are not only common in our exams, but they also help us understand how polymers behaves under different conditions. Today I am going to explain four key concepts: enthalpic relaxation, bright field and dark field imaging, 2D XRD spectrum, and the difference between tear test and tensile test. I will be breaking each topics down in a simple and clear manner so that even the more complex ideas becomes easy to understand. So let's begin. First of all, I am covering the enthalpic relaxation. Let me start by explaining what enthalpy relaxation actually is. When a polymer is cooled very quickly below its glass transition temperature, the molecular change does not get enough time to adjust into a stable configuration. So the polymer enters a glassy state that is not fully relaxed. It contains extra internal energy which we called frozen in enthalpy. Now, when we heat the polymer gain close to Tg, it begins to release the stored energy. This release of excess enthalpy during reheating is what we call enthalpic relaxation. Okay, so now I'm coming on the why does enthalpic relaxation occurs. So well, it all begins with the cooling history of the polymer. If cooling is slow, chains have enough mobility to find a stable, lower energy arrangement. But if cooling is rapidly, or if the polymer has edged below Tg, the structure becomes trapped in a higher energy non-equilibrium state. So the polymer ends up storing more enthalpy than it should. And when you later heat it, the polymer finally gets the mobility required to release this extra enthalpy. That release it is the relaxation process. Now, how does enthalpic relaxation appear in DSC? DSC means differentiation, scanning calorimetry. Okay, DSC is the full form is this. If you observe this behavior in DSC experiment, it shows up very clearly. As the polymer is heated right before or around its glass transition regions, you will see a small endothermic peak. This peak represents the release of frozen in enthalpy. It is basically the polymer recovering from the non-equilibrium state and moving toward equilibrium. So whenever you see a sub Tg endothermic bump in a DSC cover, it is signature of enthalpic relaxation. Now, what happened at the molecular level? So I'm going with the molecular level. When the polymer is reheated, the molecular segments gain mobility, free volume decreases, chain packaging becomes tighter, and the overall internal energy of the system reduces. It's like the polymer recognizing itself into a more comfortable and stable arrangement. This microscopic arrangement of chains as they approach equilibrium is the real essence of enthalpic relaxation. Now now the part is connection between enthalpic relaxation and physical aging. Enthalpic relaxation is also deeply connected to physical aging. Polymer that has been stored below Tg for a long time gradually becomes denser, stiffer, and more brittle. This slow structural change also results from the polymer trying to reach equilibrium over time. When such an aged polymer is heated close to Tg, it releases the enthalpy stored during aging, and this release again appear as enthalpic relaxation in DSC. So physical aging and enthalpic relaxation are two sides of the simple phenomena. same phenomena. One happen over time at lower temperatures, and the other becomes visible when we heat the polymer. Okay, this is the done. But if I'm going to the summary or short notes on the short explain the short language, so we can say enthalpic relation is the release of frozen in enthalpy when a non-equilibrium glassy polymers move back toward equilibrium during reheating, and it appears a small endothermic event near TG. This concept helps us understand polymer aging, stability, thermal history, and glass transition behavior. Okay, now I'm just go now this is the enthalpic relation is done. I'm coming on the bright field and dark field imaging. Before we compare the two, let me first explain what these imaging modes actually are. Both bright field and dark field imaging are contrast techniques used in optical microscopy and electron microscopy, especially TEM. Their main purpose is simple: to create a visual contrast so we can understand the internal structure of the material. But the way each technique forms contrast in is completely different, and the difference is what gives each method its unique application. Hmm. In bright field imaging, the microscope forms the image using the transmitted beam, the light or electron that pass straight through the sample. Where the sample is thick or dense, more of this beam is observed or scattered, so these areas look darker. When the sample is thin or less dense, more beam passes through, so those regions look bright. Okay, so the entire image becomes the simple map of thickness and density. Let's a very natural, easy to interrupt imaging mode. That's why bright field is the most common used techniques in basic microscopy. So now, how does dark field imaging work? So dark field imaging works the opposite way. Okay, instead of using the transmitted beam, the microscope blocks is completely the image is formed only from the scattered of or diffracted beams, the beams that are bent by tiny features inside the sample. So the background becomes completely dark, and only the regions that scattered strongly appear bright. This makes dark field imaging extremely sensitive to structural imperfections like dislocations, small particles, crystalline defects, and edges. Okay, if bright field fails you the overall pictures, dark field focus on the fine details that normal imaging would hide. Okay, so now why do we use both bright field and dark field imagings? The reason we use both techniques is because each of the highlight different features. Bright field tells us about general morphology, the shape, size, and thickness variation of the specimen. Dark field tells us about find microstructural details like especially defects on and orientation that are not visible in the bright field. Obviously, you can see or you can thought this phenomena. So, in research, we often look at the same symbol in both imaging modes to get a complete understanding of its structure. Now, a simple way to remember these differences. So we can say a very easy way to remember the two modes in this. A bright field image comes through from the frame from what passes through the sample. Dense area looks dark, but in dark field image becomes from what is scattered by the sample. Defects look bright. If sometimes scattered strongly, dark field highlight is beautifully. So you can remember in this manner. So now I'm going with the summary of this dark field and bright field imagings. So bright field uses the transmitted beam and gives us an overall view of thickness and density, but the dark field uses the scattered beams and really reveals fine details like defects, dislocations, and small particles. Both imaging techniques completed each other, and together they provide a complete understanding of the microscopic microstructures level. Okay, now this is the also covered. Now we come through the 2D XRD spectrum. So let me start with what is 2D spectrum actually is. So normally when we think of X-ray diffractions, we imagine a simple plot, intensity versus angle. But a 2D XRD spectrum is different. Instead of giving us just a single curve, it captures the entire diffraction pattern on a flat detector. This creates a two-dimensional image that contains far more information about the material, not only which phases are present, but also how they they are arranged, how oriented they are, and how uniform the crystallinity is. Okay, so why do we use a 2D XRD spectrum? The reason we use 2D XRD is because materials, especially polymers and fibers, are often anisotropic. Anisotropic means that their structure is directionally dependent. This is the basic correlation with anisotropic. So a normal one-day scan average everything together. So you lose a lot of diffraction based informations, but a 2D pattern keeps all of that. It tells us whether the crystal are not randomly arranged or aligned, whether the sample is isotropic or oriented, and whether different phases are present in different directions. So for films, fibers, microcomposites, not microstructures. Okay, thin coatings, basically anything with orientation, 2D XRD becomes extremely valuable. You can imagine it. How now I'm coming on the how does a 2D XRD pattern look, and what does it tell us? Okay, a 2D XRD pattern often looks like a set of rings or arc on the detector. If the ring arc is perfectly circular, it means the sample is isotropic. The crystallates are oriented in all direction space equally. Okay, and this is the meaning of circular if we getting in on the detector. But if the ring becomes arcs or the intensity gather is in specific directions, that tells us the material is oriented. This is very common in stretch films, drawn fibers, polymer steps, and materials processed under flow. Sharp, bright arcs indicate high crystallinity and strong orientations, while diffuse, broad rings indicated lower crystallinity or more amorphous content. Now, I'm coming on the what information do we get from a 2D XRD spectrum. From a 2D spectrum, we can extract several important species on of informations. We can see crystalline orientation directly from the shape of the rings, and the second one of the we can measure the degree of crystallinity from the intensity distribution, and third one of the we can identify different crystal phases because each phase produces its own diffraction features. So okay, we can study and the last information we get we can study texture which tells us how the crystallites are arranged directionally. So instead of collapsing all the information into one curve, a 2D XRD spectrum keeps the entire scattering image and lets us analyze the material at a much deeper level. So why is 2D XRD better than 1D in many cases? The main advantages is that 1D scan average out out everything. If the sample is oriented 2D, a 1D scan cannot show the direction of the orientations. It only shows intensity versus angle. But a 2D pattern preserves all directional information. Let's like the difference between looking at a location on a map as a single point versus seeing a full aerial image of the sample place. One gives you numbers, the other gives you the whole picture. You can relate like this. Okay, I'm going on the overall the 2D spectrum. 2D XRD spectrum. A 2D XRD spectrum is useful diffraction imaging that shows crystallinity, phase, and especially orientation in a material. It is extremely useful for polymers and fibers because it captures details that a 1D XRD scan completely hides. If you want to study textures, anisotropy, or processing effects, 2D XRD is one of the most powerful tools available. So now 2D XRD spectrum is also done. Now I'm coming on through the last one, tensile test and tear test. Okay, so before comparing both tests, I want to quickly explain what the tensile test tell us. Tensile test is basically the most fundamental way of checking how a material behaves when we pull it in one direction. In this test, we stretch the specimen slowly and uniformly, and the machine keeps recording how much force the sample can take and how much it elongates before breaking. So from this we get very important mechanical properties like tensile strength, elongation at break, Young's modulus, and overall ductility of the material. Okay, a simple terms, a tensile test tells us how strong and how stretchable a material is under smooth uniform pulling. So now let's understand what is tear test. Okay, means on the other hand, a tear test is designed to measure sometimes some things very different. Instead of pulling the whole material uniformly, where here we force the material to tear from a pre-existing cut or notch. Why do we do this? Okay, because in real life materials like rubber, plastic films, gloves, and packaging rarely fail because someone stretched them evenly. They fail when a small cut or crack starts growing. So a tear test focuses on the exact scenario. It tells us how easily or how strongly a material can resist the propagation of a crack. If a material has good tear strength, even if a cut is present, the crack won't spread easily. This is the very important part. Okay, I mean, I'm coming on the how the two tests differs is in what they present. A tensile test represents uniform stresses. It tells us the overall strength of the whole material's body. But a tear test represents localized stresses starting from a defect. It tells us how the material behaves, like when it is forced to tear at a weak point, and the difference is huge. A material can use excellent tensile strength but still have very poor tear strength. For example, many stiff plastics are strongly when stretched, but the moment a small notch appears, they tear very easily. Uh, why do elastomers and films needed tear test more? This is the most important parts to understand tear test and tensile test. In elastomers and soft materials, crack growth is a big concern. Okay, things like rubber sheets, tires, glass, footwear components, and polymer films always face cuts, stretches, and edge defects during use. So for these materials, tear strength becomes a more practical property than tensile strength. A material with high tear resistance performs which much better in daily life, even even if its tensile strength is not the highest. Now, how each test looks in real lab conditions. I'm covering on the lab. In this tensile test, the sample has a smooth dumbbell shape, uh, and the stress spreads evenly throughout. The failure usually occurs in a middle, and the specimen stretches a lot before it breaks. But in the tear test, the specimen has a notch, and the cracks starts exactly from that point. The machine pulls the sample apart, and B measures how much force is needed to keep the tear growing. The tear test failures is fast localized and crack driven, while tensile test failures is slow, uniform, and stress driven. So finally, this is the done. Now I'm just giving the summary of this part is also. So you can understand, tensile test tells you how strong a material is when you stretch it smoothly. Tear test tells you how resistant a material is when crack tires to grow through it. One measures overall strength, the other measures crack resistance. Now this is the final ending of my video. So all these concepts play an important role in understanding how polymers behaves thermally, structurally, and mechanically. Today we covered four key concepts: enthalpic relaxations, bright field and dark field imagings, 2D XRD spectrum, and the comparison between tear tests and tensile tests. I genuinely hope this video helped you understand these ideas a little more clearly. So since I have just started making such videos, if you notice any mistakes, I kindly request you to please forgive me, and your support and feedback mean a lot to me, and they really help me improve further. So thank you so much for watching me, and I hope to see you again in the further next video. Thank you.